Welcome back, everyone. Today, we've got a truly incredible explainer lined up for you. We're looking at a brand new release from NASA that honestly feels like something straight out of a forensic crime novel. Except, well, this one is playing out millions of miles away on the surface of Mars. Okay, let's dive into this. We're investigating the Martian climate mystery, and specifically, how these tiny, microscopic crystals are acting as the ultimate clues to unlock the secrets of our neighboring planet's ancient past.
So, we have to set the stage here first. Thanks to decades of satellite imagery and rover exploration, it's pretty much a well-established scientific fact that ancient Mars wasn't always the desolate, frozen landscape of dry, dusty dunes we see today, right? Once upon a time, Mars was incredibly dynamic. It had flowing rivers, expansive lakes, and a climate that actually supported liquid water right on its surface.
And that brings us to the core mystery of our investigation today. Yes, we know the water was there, and we know it transitioned into the dry dunes we observe right now. But when exactly did it dry up? And perhaps even more importantly, how fast did that massive environmental shift happen? For years, there's been this lingering uncertainty over the exact timing of these changes. We really needed a timeline. But you know, rocks on a dead planet don't just hand you a calendar. You have to know exactly where and how to look.
Which brings us to part one, the detective and the clue. Because to solve a mystery of this magnitude, you absolutely need a brilliant detective. Our lead detective in this case is NASA's Curiosity rover. Curiosity has been hard at work rolling through Gale Crater, which is this massive ancient impact basin. But Curiosity isn't just taking pretty pictures up there, it's getting its hands dirty. Using its robotic arm, the rover drilled into the Martian rock and delivered 20 specific powdered rock samples straight into a highly specialized tool on board. It's called the Chemistry and Mineralogy Instrument, or CHEMIN for short.
Now, what's really interesting about this is the distinction between looking at Mars from orbit versus looking at it right there in the dirt. As Tom Bristow, the principal investigator of the CHEMIN instrument, points out, satellites are great for the big picture, but they just can't tell you about the dimensions of a single microscopic crystal. CHEMIN uses X-ray diffraction. It's literally shooting X-rays at rock dust to see how they bounce off the atomic structures. This gives us ground-level robotic data that is fundamentally unique. It's this exact microscopic view that cracks the case wide open.
And that brings us to the clue itself, hematite. So hematite is an iron oxide mineral. Why do we care about iron oxides? Well, because they form in the presence of water. They are literally the chemical receipts of ancient water activity. But the scientists at NASA realized something profound here. Hematite doesn't just tell you that water was there. Its physical shape, its structural size, acts as a mineralogical fingerprint. It's an actual, readable indicator of past temperatures and climate conditions.
Okay, let's move to part two and see how this builds. Reading Gale Crater. Let's examine the exact scene of the crime.
Picture Gale Crater, kind of like a massive canyon or a deeply carved gorge here on Earth. The crater walls are stacked with layers of rock. And in geology, depth equals time. The higher you are on the crater walls, the newer the rocks. But the deeper you go into those lower elevations, the further back in time you're traveling. You're capturing the absolute earliest years of Mars's environmental history. It's quite literally a vertical timeline just waiting to be read.
And this brilliantly illustrates the stark forensic contrast the Curiosity rover discovered. Let's compare the layers. On the left, up in the higher, newer elevations, the hematite crystals were tiny, like less than 10 nanometers. They also found another mineral hanging out alongside it called goethite. But look at the right side. Down in the lower, older layers, the hematite crystals were massive in comparison, reaching up to 65 nanometers. And the goethite? Completely absent. This isn't just some random anomaly, guys. This is a very specific chemical reaction frozen in stone.
Section 3. The Science of Size. Let's look at exactly how this microscopic size translates into a macro understanding of the climate.
The secret behind the crystal size comes down to a fascinating physical process known as Ostwald ripening. Imagine you've got a bunch of small ice crystals in a slightly warm freezer. Over time, the smallest ones melt and refreeze onto the bigger ones, making them grow. Well, in geology, Ostwald ripening works in a very similar way. Smaller mineral crystallites literally dissolve and donate their material to help the larger crystals grow. But here's the absolute key to all of this. This process strictly requires warm, wet conditions to happen.
Let's walk step by step through exactly what happened deep in the layers of Gale Crater. Step 1, you need water that's warm and it has to have a neutral or slightly alkaline pH. If you've got that, step 2 triggers. Remember that goethite mineral we mentioned earlier? Well, under these warm conditions, it actually transforms entirely into hematite.
That is exactly why goethite was missing from the lower layers. Then, step 3, Oswald ripening kicks in, dissolving the smaller hematite bits. And finally, step 4. The big crystals gorge themselves on that dissolved material and grow all the way up to 65 nanometers.
Now, I want to pause for a second and just emphasize the extraordinary scientific fidelity it takes to pull off this level of microscopic detective work. Ashwin Vasavada, the Curiosity project scientist, points out that the rover's Chemin instrument doesn't just broadly scan and say, hey, there's some hematite over here. No, it extracts the exact size, the specific shape, and maps the related minerals down to the nanometer. That precision is literally the only way scientists could definitively prove that Oswald ripening occurred on Mars.
Which brings us to our final section, a habitable ancient Mars. We've got our clues, but what does this all mean for the big picture? Well, if you look at the newer top layers of Gale Crater, the crystals are tiny. That tells us the water near the surface was either way too cold or it evaporated too quickly for the crystals to grow. But down in those lower layers, those big 65 nanometer crystals act as undeniable proof that the warm water didn't just flash through. It was long-standing, it stuck around, and it stayed warm enough for this incredibly intricate, slow chemical process to fully play out.
So just how long is long-standing? Well, the NASA team suggests that this warm groundwater might have remained in the deepest layers of Gale Crater for up to 4.7 million years. I mean, just think about that staggering number for a second. While the surface of Mars was undergoing massive, drastic shifts, potentially losing its atmosphere and turning into a frozen desert, deep underground there was this stable, warm, wet environment lasting for nearly 5 million years.
So the crucial point is perfectly summarized here by Tanya Peretyashko, a planetary scientist at NASA's Johnson Space Center. The timeline of Mars drying up, it isn't just a simple straight line. The surface climate was becoming colder and harsher, absolutely. But these buried rocks were acting like insulated protective blankets. They housed warm and wet conditions for extended periods right beneath the surface. All right, let's summarize the final verdict of our investigation. First, NASA has successfully proven that the crystallite size of hematite can be used as a literal climate thermometer for ancient worlds. Second, by reading this thermometer, we know for sure that the deeper layers of Gale Crater hid warm, neutral pH water. And third, and honestly most excitingly, because these deep underground aquifers survived for up to 4.7 million years, provided other essential elements were present, they could have offered potentially habitable conditions long after the surface of Mars became deadly.
It completely shifts how we view the history of Mars, doesn't it? It really makes you wonder, if Mars was able to hide warm, potentially habitable aquifers deep underground for millions of years while its entire surface froze over, what other incredible secrets are just sitting there, waiting to be drilled into inside the rocks of our solar system? Science is an incredible detective story, and we are clearly just on the very first chapter. Thank you so much for joining me for this explainer. Stay curious, and I'll see you next time.